Today we're going to take a look at accuracy and precision and the very related concepts, which are random uncertainty and systematic error. So ordinarily in everyday life, accuracy and precision mean the same thing to us. But your English teacher might use them quite properly. She might read a sentence out of your essay that looks like this and say that is a very precise statement, meaning that you've got lots of adjectives in there. You're very precise in what you're saying. You're not using words like thingamajig and stuff. So that's a precise statement. But she might also say that it's not accurate. And that would be because it wasn't really a metaphor, for instance. You were on the wrong track, but you were saying something very precisely. Shaq O'Neal, I think he was a very precise free throw shooter. He just wasn't a very accurate free throw shooter. That's because he shot the ball with almost no arc at all. So the ball would take a very flat trajectory and then hit the back of the rim and bounce off. And almost every single shot would do that same thing. So he was precise because he always hit the same spot. He just wasn't very accurate because he wasn't getting the ball into the basket. Now, accuracy and precision, very related to what are called systematic error and random uncertainty. And in fact, it's systematic error that causes poor accuracy. What's meant by systematic error? Systematic error is when all your measurements are shifted off in the same direction. And so this might occur when you are using a micrometer. Here's a micrometer. If you turn this knob around and you close this, you should get a reading of 0. If it's not quite reading 0, then all your measurements are off because the micrometer is poorly calibrated. And in fact, this little knob right here, that's for recalibrating your micrometer. And then you're probably familiar with weigh scales. Sometimes you have nothing on the weigh scale and there's still a reading there. And that's when you press the tare button so that you can zero your weigh scale. So systematic errors shift all the data in one direction. And ideally, such as in the two cases above, we're going to be able to correct for that. But there's a lot of circumstances where you don't know how big the systematic error is, so you can't make that correction. And there's a lot of situations where there's a random aspect to your systematic error, and that makes it very hard to control as well. So systematic errors throw all your results off, and they lead to low accuracy. So you want to make that very strong connection between systematic errors and accuracy. Now, the thing that causes poor precision is random uncertainty. So let's say we're doing an experiment and we're dropping some balls and we're measuring how much time it takes to hit the floor. We would find that there was quite a bit of fluctuation from one reading to the next for exactly the same measurement. And in this case, it would largely be caused because your human reaction time is not consistent. There's a very strong random element to your human reaction time. However, if you were to take enough measurements, keep repeating and repeating the same measurements, the average should converge towards the true value. So this random uncertainty, it is the cause of low precision. So let's start off with an example that has both low accuracy and low precision. So let's say we've got a stopwatch and we're timing how much time it takes for a ball to fall by 5 meters. We do 5 trials, we get these values right here, and they're averaging 1.032 seconds. The true value for this measurement is 1.01 seconds. And now as we look a little bit farther, we find, oh, whenever we start our stopwatch, it's starting at 0.03 seconds. So our values are all too high by 0.03 seconds. So in this case here, we've got low accuracy, meaning that because of that systematic error, all of our values are away from the true value, the target value. We've also got low precision. So you can see large fluctuations in these values right here. And that's largely going to be caused by human reaction time. So that we're not only shifted a long way from the true value, we've also got a wide spread in our values. So the width of these values is kind of a measure of our random uncertainty. So let's say we correct for the systematic error. We're going to subtract 0.03 seconds from all the times. So here are the new adjusted times. and our average time now is 1.002 seconds. But of course, we haven't changed the precision. We haven't changed the random uncertainty. So what's going to happen now is we're going to have a whole bunch of values that are going to circle the true value. So you have very little systematic error, but you still have low precision. You still have values that are well spread out. So let's make another correction. And let's say we put in a photogate timer. We're going to eliminate that human reaction time. And let's say our values come out to be like so. So now you can see the values are all tightly bunched together. There's very little range in there. And that means that when we look at our data on here, not only are they going to kind of circle the true value, they're also going to be very close to the true value. So in the end, what we want to do is to get our systematic error as small as possible and get our random uncertainty as small as possible so that our values are going to be as close to the true value as they can possibly be. Okay, let's very briefly summarize the video. First thing I want to talk about is mistakes. In general, do not write about mistakes in your lab. If you read the units incorrectly, or you somehow changed your measuring technique, or you made a mistake in your calculations, don't write about that in your lab, because it just tells the reader that you're not very good as an experimenter. So you either want to declare that measurement an outlier, or you want to redo your calculation, etc. Now, no matter what equipment you use, there's always going to be random uncertainties and systematic errors. So another thing is, do not complain. No complaints. Don't complain about the equipment. Whatever equipment you're using, it is limited. And you want to say how big are those limitations, and you want to suggest some improvement for those limitations. And that's it. Don't get into the complaining mode. Now, generally the way that we improve random uncertainty is to improve the measuring technique, such as going from a stopwatch to a photogate timer. Random error, that is random uncertainty, can be reduced by repeated measurements, but you can't do that with systematic error. Large random uncertainty always produces low precision, whereas large systematic error produces low accuracy. And in very simple situations, you can correct for the systematic error. And that's kind of ideal, but that's not always possible. And I have one IB multiple choice question for you. Please stop the video, read it over, try it out, and then come back for the answer. Hopefully you said the correct answer is A, that is that you can be very imprecise but still accurate. And that would be when you have a large spread in your values, a large random uncertainty, but very little systematic error. And then part B, measurement that is precise is always accurate. Well, not necessarily so. So you could be very precise, but you're missing the bullseye. You're not near the true value because of a systematic error. C, a measurement that is not precise will always be inaccurate. That's not true at all. You might have a very imprecise measurement, but they do circle around the true value. And that's because you have a low systematic error. And then repeated measurements, they will always increase accuracy and precision. Well, yes, they do increase precision, but they don't increase accuracy because systematic error will not be corrected for. And that's all for today, folks. Thank you very much.